So now, in part C, we will take into account the humidity of the air. So the things will get a little bit more complicated because we don't have the same ratio between the quantity of dry air and of moisture in the air we have inside the workshop and outside. It is given in your exercise that the relative humidity is equal to 50% inside and to 50% outside. But because we don't have the same temperature and the relative humidity is relative to temperature, in terms of quantity or in moisture content, we don't have the same moisture content, and as we will read on the psychrometric chart, the moisture content is much higher inside the workshop than outside. So this can come from, for example, many people working in the workshop, because when people are breathing, we are increasing the humidity of the air, but the difference is so big that inside the workshop there are probably machines, for example dryers, that are rejecting moisture to the air we have inside the workshop, and that's probably one of the reasons to have a high mass flow rate of air renewal from this workshop. So now we have a few changes. So the first one is to consider the relative humidity we have inside and outside, so 50%, and also concerning that now the mass flow rate of air that is taken from the workshop and renewed from fresh air. We consider that it's only the mass flow rate of dry air. This is so an approximation here, or new data from for the exercise, and we always choose when studying moist air the reference of mass as being dry air, because usually in a process the mass flow rate of dry air is not changing, but the total mass flow rate might be changing if there is, for example, evaporation of condensation or condensation of water. So we will once again study what's happening at the inlet and outlet of the heat exchanger, and in order to simplify or to be more clear into the developments we'll do, I have given new names for the inlets and outlets of the heat exchanger. So the inlet of stale air is A, the outlet is B, the inlet of fresh air is C, and the outlet is D. So now we are sure we cannot really mix up about what we are talking about. In this new part, we consider that the calculation of 18 kilowatts here for the heat transfer rate between the fluids in the heat exchanger remains true. But we will see what's going on with the state, and especially the moisture content of the fluids of the both kinds of air when this heat transfer is taking place. So in order to do that, we need to calculate the enthalpy variations we have between A and B and between C and D, so that we get this enthalpy difference for both fluids. So we can do a heat balance, and the heat flux or heat transfer rate that is received by the fluid is equal to its mass flow rate multiplied by the specific enthalpy. In moist air, this specific enthalpy is expressed in energy per unit of mass of dry air, so that's why it's multiplied by the mass flow rate of dry air. From the point of view of the hot fluid, the heat transfer rate that is received is minus QHE, because QHE is defined as the fluid that is given by the heat that is given by this fluid and not received, and here it's positive for the point of view of the cold fluid. So we can calculate this variation of specific enthalpy. So HCD is equal to delta minus delta HAB, and it can be calculated as 19.6 kilojoule per kilogram of dry air. Let's now see what it means on the psychrometric chart about the variation of the states of the cold air and hot air.